Okay. In the previous video, we talked about the Fisher's inequality, which is about subfamily where pairwise intersection has always constant size. Now, we want to generalize that. Okay, so we're going to define L-intersecting family. So let's say L be subset of the integers. Then we say a family F of sets is L-intersecting if for all x, y in F, x intersection y is in L, right? So if L has cardinality 1, then we could apply Fisher's inequality. Yeah. Right. Now, what can you say? Right. So what happens? So how large can F be if it is L-intersecting, where L has size S? Since this is like reasonable question. So one instance is when L is 0, no, not 0. Yeah, okay, 0. So example, so 0, 1, 2, up to S minus 1. Then we take F to be the set of subsets of size at most S, right? If you take all these sets, then pairwise intersection has size at most S minus 1, so therefore it is L-intersecting. In this case, cardinality of F is sum of these binomial coefficients from 0 to S minus 1. So this could be a lower bound, right? So if we're gonna prove any theorem about the upper bound of the size of L-intersecting family, then this could be potentially the number. And that is the theorem. So let me say theorem 1. And this is due to Frankel and Wilson in 1981. If F is an L-intersecting family of subsets of 1 up to n, then cardinality of F is at most this number. And it doesn't matter what L is, as long as L has size S. Oh, yeah. I should say L has size S. We're going to prove it later, and I will show you many other variations. And second variation is what if F is uniform, right? If F is uniform and L-intersecting, what can you say? Then we cannot take all subsets of size less than or equal to S, because we only need to take, we can only take a set of size, same size. So we could guess like n choose S, right? Because we can take all subsets of size S, and if this is our set L, then there exist n choose S subsets, which is L-intersecting and it's uniform. And is this best possible? And theorem is yes. Yes, it is. So it's raised Zadhuri and Wilson in 1975. So I think I can almost copy, but anyway, if F is an L-intersecting uniform family of subsets of 1 up to n, and size of L is S, then cardinality of F is the most n choose S. Oops. Yes, so that's the second theorem that we will discuss, proof later. So let me remind you that a family is uniform if all members have the same size. Now, that's not all. Now I want to tell you more versions, more variations. So what if, like, instead of L-intersecting, we could generalize that further. So instead of, so what if we ask x intersection y is in L modular P? So what that means is the cardinality of intersection is in L up to modular P. So when you divide by P, the remainder is in L. So this could be so let me write L plus P, that, right? So this is like all, I mean, you know what it means, right? This is all the integers which has the same remainder as some integer in L by when you divide by P, right? So in other words, it's A plus P times I, where I is in G and A is in L. All right, so now this is the third theorem. So there's and Frankel and Singh in 1983, and we only prove it for prime case. You will see later why it's nice to see the prime case. And let L be a subset of these numbers, and size of L is S. Now we have two conditions in order to make the theorem works. For every A in the family, the cardinality of A is not in L plus PZ, and A intersection B is in L plus PZ for all distinct oh yeah, I forgot to say that A is a family. No, F is a family. The F be a family of subsets of 1 up to n. Right. So what's gonna be the worst case? I think this. I mean, you can see that this is analog of Frankel and Wilson's theorem, right? Let's look at here on the left-hand side, right? So if L is 0 up to S minus 1, then what you can do is to take all subsets of size at most S. And actually, even in this modular version, you have the same bound. Okay? And why is this interesting? Because remember, in the first lecture of this course, there was an odd club problem, right? So for any pair of clubs, the intersection has size odd. No, intersection has size even, and each color has size odd, right? And that's exactly the situation when when P is 2 and L has 0 only, right? So this is a generalization. Now, so this is analog of Franklin-Winsor's theorem. Now, what if we moreover, in addition, we require all members of this set family to have the same size? Then can we expect to have something like the second theorem? And we do. And we can actually make it more general. Instead of saying uniform, we can say the cardinality is constant K modular P. So that's our fourth theorem. So Alon, Babai, and Suzuki in 1991. So again, P is a prime, and that L be a subset of P minus 1, and size of L is S, and we assume S plus K is less than or equal to N, and F be a family of subsets of 1 up to N, and if cardinality of A is equal to K modulo P for all A in F, and K is not in L plus PZ, and A intersection B is in L plus PZ for all A distinct, then we do have the analog of the second theorem. Okay, so I'm going to discuss these 4 theorems, and each of them uses linear algebra. If you recall our very first video, it was about the linear algebra, right? Right, so let me start with the third theorem. So proof of theorem 3. Right, so theorem 3 is on the left hand side. Right. So if you remember how we prove it for odd club problem, then it's similar. So let's say F is A1, A2, AM. So these are members, and that AI be the vector, right? Now we're going to use the field FP. So this FP is a finite field consisting of 0 to P minus 1, right? And then you have addition and multiplications. And this is 0, 1 vector. So AI, say, right? Where, is that a good notation? Yeah. So AIJ. All right. So AI1, AI2, AIN, right? Sometimes we say this such a vector is a characteristic vector. Now let L be set L1, L2, Ls. And then we're gonna construct a polynomial. Right? So for I in 1 up to m, let fix is a polynomial which is defined as follows. Oh, no, I shouldn't use I, so j x dot ai minus lj. For x in p to the n. Right, so what does this mean? So for any vector in n-dimensional vector space over this finite field, or we define this product of these things, and this is inner product, right? Dot product. So imagine, like you can say, like xi times ai. No, I cannot use I. X. I cannot use j. I cannot use what is it? I, j, k, l, m, p times. Okay, whatever. Right, something like this. So what's going to happen? Well, we know that fi ai, if we plug in ai, then the cardinality, so this is going to be the product of ai.ai, which is the number of ones in this ai, so it's ai minus lj, right? And now we use the fact that the cardinality of ai is not equal to lj modulo p. So this is not non-zero modulo p, right? And if I plug in aj, so if I is different from aj, then this at some point it's gonna, okay, I shouldn't use j, but anyway. I'm running out of the small letters. ai intersect, so the dot product become ai intersection aj, and then you're subtracting lp, so this is becoming more zero modulo p. So we know that they are linearly independent, but the degree of these polynomials are too high to prove something interesting, right? Right. I mean, this already implies that f1, f2, fm are linearly independent. So let me use different color. What happens? The argument goes like, so the number of polynomial is bounded by the dimension of the subspace of polynomials containing all these vectors, all these polynomials. But these polynomials are degree s polynomials, right? So if we don't do anything, it's gonna be like, it's gonna be huge, right? It could be huge. Degree s polynomials. And how many, I mean, what is the dimension of that? Well, of course, there's a way of computing it, right? So the number of ways to select S objects from n object, allowing repetitions, right? So n plus s minus 1, choose s minus 1. No, I think it's, yeah, n plus s minus 1, choose s. But then you sum over, also you do the same thing for smaller s. So it's gonna be not very tight. So we need to reduce this vector space. How do we reduce it? And one way, and this is interesting trick. Now the trick is we obtain fi tilde from fi by replacing xj squared to xj after expanding it. Right? So we have a polynomial, we expand it. So now there will be like product of x1 times x1 times x3, or x1 times x4 times x5 and x6 and x6 and x6. And then for each of them, for each monomial, whenever you have a square, then you reduce it to a linear. Whenever you have x1 to the power, x1 to the 10 or x1 to the 9, you replace by x1. Okay? Now, why is this good? This is good because when we evaluate this polynomial with the 0, 1 vector, then the number doesn't change. So the key point is fi tilde ai is still fi ai, because square, 0 squared is 0 and 1 squared is 1. So this is going to be not 0 modulo p, and fi tilde aj, if I is different from j, this is still fi aj and it's 0 modulo p. Alright? So then we observe that f1 tilde, f2 tilde, fm tilde are linearly independent. Right? Why? Because if not, there's a linear combination. Then ci, fi, we just plug in ai, aj, then what we get is cj, cj. Okay, so just to clarify, everything is over the finite field, but fp, but to clarify, I'm writing modulo p. So cj, fj, aj is 0 modulo p. This is non-zero and p is a prime, so that's why cj is 0, and that's enough, right? So all the coefficients are 0 modulo p, so therefore in the field it's 0, right? So they are linearly independent. These are vector spaces over the binary field. No, not binary, of the finite field of size p. All right. So the dimension in all fi tilde are contained in the span of a right. You need to look at the span of all the product of distinct variables, right? Span of the multilinear, right? So linear is important. We never have a square. Multilinear polynomials of degree n most s with n variables. So just the basis of, I don't have to say basis, but these bases, right? So it's like something like this, right? It's spanned by all these things, right? So I1, I2, IL, which is less than S, and L. Yeah. So how many such monomials do we have? It's just the number of them is sum of this n choose I from 0 to s. Therefore, m is at most this, because these f1 of f1 tilde to fm tilde are contained in the subspace of dimension at most this. So therefore, and they are linearly independent, therefore the number of them is bounded by this. Okay, that's a cute proof. All right. So we have seen the proof of theorem 3. Now that's modular version. Now let's prove the theorem 1. Right, so this one. So we have an L-intersecting family, then its size is at most sum of the binomial coefficients. Here, there's no condition about the size of a member of this family. So it could be, it may be possible that some AI has size exactly some Li, some member, right? Okay, so let's see. So let's do the same constructions, right? So L is this, F is A1, A2, AM, and let AI now we use real, so R to the N, the characteristic vector of AI, and we assume these sizes are sorted. All right, and let Fix, I'm looking at the first proof, I'm doing something similar. This is product of x dot AI minus Lj, where j is from 1 up to s. But there is a danger. So the danger is that maybe some member of family has size Lj. Then this becomes 0. I don't want that. But if some member has size Lj, then its intersection with any other member will never be Lj because the intersection will be smaller. So we're going to sum over all j satisfying this condition. So Lj is less than size of AI. So that's my Fix, and let Fi tilde x be the multilinear polynomial obtained from Fix by reducing xi squared to xj squared to xj repeatedly. So whenever you have square or cubed or 4 xi to the 10, you replace it by xi. Right? So this is to ensure that Fi tilde of x is equal to Fi x for all 0, 1 vectors. Now Fi tilde AI is Fi AI, which is product of AI dot AI, which is cardinality of AI, and then we sum over all j where L is less than AI, so this is non-zero, right? And Fi tilde aj is equal to fi aj, which is product of ai intersection aj minus lj, and lj is over all j is over all j. I mean, this product is over all j where lj is less than ai, and this will become 0 because of the L-intersecting condition. So f1, f2, fm are linearly independent, and by the same logic, the dimension of subspaces, the subspace of multilinear polynomials of degree at most s is at most, I mean, it's equal, but it's enough to say this. So m is, since they are linearly independent, so m is at most that. All right, so that's the proof of the Franklin-Wilson's theorem. So when you have an L-intersecting family, then the number of them is small. All right. Oh, maybe I'm cheating here. All right, so why is this 0? Why is this 0? So if you haven't noticed my cheating, then now it's time to think about where it can go wrong. Right? So there's one little case. What if AI intersection AJ has exactly sized AI? In that case, and this could be equal to LJ, right? Oh no, not LJ. Oh, I'm not supposed to use same index J. So okay, that's let's replace J. This J by, oh, this is a J, right? This is LK, right? So it's a sum over K. Now, the thing is, if AI intersection AJ has size rejected AI, so which means the AI is a subset of AJ, right? In this case, it is possible that this intersection is LJ and this polynomial is non-zero. That's a danger, right? So that is dangerous. But we know that if this is the case, then AJ, so AJ is a AI is a proper subset, so AJ is definitely bigger. So J, since we sort the elements, now we use this fact. Oops. We have sorted these members of F in an increasing order. So therefore, in order to have this kind of situations, we will have J bigger than I, strictly bigger than I, right? So now, in order to make equality, then you need to have for I bigger than J. All right. But still, this is enough to prove that these are linearly independent. Right, so let me show. Still, f1 tilde, f tilde. Okay, so let me show you. Yeah, fm tilde are linearly independent. Why? Suppose cifi tilde x is 0.
알겠습니다.
Now what are we gonna do? And now if yes, so if I is bigger than j, then this is 0, right? So if I put x to be a1, then I know that c1 f1 tilde a1 is 0, right? If x is a2, then I know c1 f1 tilde a1 plus c2 f2 it's 2. Let me just explain. Right? So it's like a lower triangular matrix. Yeah, and then I have to write everything. But the thing is, the first equation implies that C1 is 0. And the second equation, since C1 is 0, C2 is going to be 0. And if C1, C2 are 0, then C3 is 0, etc. So inductively, all CIs are 0, right? What I mean, if I want to write this as a correct inductive proof, if C1, C2, C3, CK is 0, then I know that CI, CK minus 1, AK is 0, so this implies that FI tilde A, FK, AK, CK is 0, so this implies that CK is 0. Right? So inductively, this implies that all of CIs are 0. All right, so that's the situation. Yeah, so that's why it was a nice idea to have sorting, right? And then we have instead of having something like a diagonal matrix, we have now something like a lower triangular matrix, which is still linearly independent. Okay, now we have seen the proof of theorem 1 and 3. All right, now let's see the proof of theorem 2, which is generalization of this art club situations. So, right, so f is L-intersecting and uniform, and L has size S, then we want to prove that size of f is at most and choose S. Right? So let K be the cardinality. So let A1, let F be A1, A2, AM, and K be the size of them. All right. And now we construct all these same thing. So AI be the characteristic vector. Right? And L is L1 up to LS. And we may assume Li is less than K because the intersections will have size less than K. So let Fix be the product of x dot AI minus Lj. For x in Rn. Okay. Now we do the same thing. Fi tilde be the multilinear polynomial obtained from Fi by reducing xj square to xj repeatedly. Then Fi tilde x is equal to Fi x for, okay, so far these are same, very much repeated. Now by the same logic we know that they are linearly independent, but that doesn't give us a good bound, right? So we need to have something else, right? So we know that f1 tilde, f2 tilde up to fm tilde are linearly independent because we know that fi tilde ai is non-zero and fi tilde aj is 0, right? In this case, all the intersections have size less than k, so nothing to worry. So this implies, yeah, that f1 tilde, fm tilde are linearly independent, but that only gives you the bound that m is less than or equal to sum of the n choose I, where I is from 0 to s minus 1. But what we are trying to prove is stronger than that, right? N choose s. Now, what we are gonna do is add more vectors into this thing, and for each subset I of size I of okay 1 to s with size of I, oh yeah, actors is n s, we're gonna construct the polynomials. Gi of x be the polynomial where this vanishes whenever xi is a characteristic vector of a set of size k, and then product of xi where I is in I, right? The feature is that if x, so this, the idea is that if gi, so if x is a characteristic vector with x dot x is k, then gi of x is 0. That's the idea. Now again, let gi tilde of x be the multilinear polynomial obtained from gi by reducing xj squared to xj repeatedly for all j. Alright, now we have a multilinear polynomial, and number of them is sum of the binomial coefficients n choose 0, n choose 1 up to n choose s minus 1. So now you guess what we're gonna do. Claim is f1 tilde, f2 tilde, fm tilde, and gi for all I in I less than s are linearly independent. How do we prove that? Suppose that alpha I fi tilde plus beta I gi tilde is 0 for all x. All right. Now, by taking x is equal to ai, we know that alpha I fi ai, and the gi tilde term will vanish because gi tilde ai is 0. And this term is just nothing but, oh, I am using, okay, let's say this is aj. So this becomes alpha j and fj aj. And I can remove tilde, and this is non-zero. Oh, this becomes 0. So that means alpha j is 0, right? So this was 0, so it implies that alpha j is 0. And so that means all alphas are 0. Now we need to look at the beta terms, right? So among all, so if there is I such that beta I is non-zero, then choose I that is minimal among them, right? By minimal, I mean beta I is non-zero. Okay, let's say choose I0. Right, so beta I0 is non-zero, and for any proper subset of I0, beta value is 0. Okay, now let x star be the characteristic vector of I0. Okay, now let's look at the value of this. This is x star, right? So this is the, what is it? This is I0 minus k times product of xi. Right? In I. Now, as soon as you have 0 in any of these, so this is 0 if I contains any elements outside of I0, right? Yeah, so in order to have this non-zero, then I has to be a subset of I0. But we know that for any proper subset of I0, the beta value is 0 because we chose I0 to be the minimal one. So that means beta I0 and G I0 tilde X star is 0. And this implies that beta I0 is 0. Alright? So that's contradiction. So this proves that these vectors are linearly independent. So therefore m plus number of them, and choose I from 0 to s minus 1 is less than or equal to the dimension of multilinear vector spaces. Dimension of vector space of multilinear polynomials of degree m most s, right? Which is sum of n choose I from 0 to s. So therefore m is less than or equal to n choose s. Very nice proof, right? Right, now we have a one theorem left, right? The one theorem which we didn't prove yet is Alomba-Suzuki's theorem. And for that, we require some setup. So let me stop this video and explain that in the next video.